opposite. When you encounter two nodes, you merge them. So as you're going down to find what to delete, you merge things together along the path you're going down. So what you're doing is making sure you're not going to leave any holes. So by the time you get to the end, to the leaf that you want to delete, when you remove it, it's just one operation to refill things in, redistribute things, and change the level of the tree at all. But you are guaranteed you have room because, or you're guaranteed you didn't leave holes because you were merging things as you went down. And this eventually means that when your root is a 2 node, as soon as you try and delete and hit your root, you're like, oh, you're a 2 node, you need to merge. And so you merge it down with one, the left or the right child, depending on where you're going, and you reduce the length of the height of your tree bundle. So that again maintains that balance because you only add or remove from the root. The book goes through in detail all of the steps and shows you a lot of stuff like this for doing remove. But we don't have it in the slides. Okay? So that's 2, 3, 4 tree. Any questions on the 2, 3, 4 tree? Did you guys think that that was more cool than the 2, 3 tree? Yes.
Yeah.
Yes? Okay, good. Because we don't use those either.
All right.
God dang it. So many things. All right.
What are we going to learn about?
We're getting there. No. Okay, so we don't use these. One of the problems with 2, 3, and 2, 3, 4 trees is they're not binary trees, and we like binary trees because they only need 2 pointers and they're easy to use. All right, so somebody decided they invented something called a red-black tree. A red-black tree is a binary search tree, which is nice because I can binary search on it. But a red-black tree is a binary search tree that encodes or represents a 2, 3, 4 tree. And so, what is one of the principles of a 2, 3, 4 tree?
Always stays balanced.
Always stays balanced. So red-black tree is a binary search tree that represents a 2, 3, 4 tree, so that means it's always balanced. So red-black tree is an always balanced binary search tree. So it retains the advantages of a 2, 3, 4 tree, but you don't need the 4 pointers and you don't have to do the check 3 different things every time you're doing a search. You just have one value in each node because it's a binary tree and you go this way or this way and you find it, okay? So, how do we actually do this? This diagram is awful. I complained several times already, and I'll keep complaining. These slides are so much worse than the 5th edition slides, which I think are probably still on the, yeah, they're still on the
beginning of that read.
Yeah, okay, great. So, I don't know why they messed it up.
That's what it is in 7th edition.
Same as the 7th edition? Yep. Yeah, okay. All right, so what they didn't show you here is, so with a red-black tree, the nodes are not colored. It's not that's not where the color comes in. The color comes in the edges. The edges that connect nodes. Every edge has a color. It's either red or black. Red, black, green. Okay? The red edges mean that I am connecting nodes that in the equivalent 2, 3, 4 tree would be in the same node. Black edges are used to point out children in the original 2, 3, 4 tree. So here, what kind of node is this? 4 node. It's a 4 node. So I have 3 siblings that are connected like this. That's a BST, right? But I'm using red edges to show that parent relationship. And then these are the children, these subtrees, and I use black edges for that. Okay? Now, obviously in memory, there's not color. So you just, generally what will happen, people just use an actual flag that says what color is my pointer here, what color is my pointer here. There's some tricks that people can use for this. But the idea, though, which you might not understand why we want to do this, but you'll be clear soon. The idea is that I use the red pointer for the within node, and then I use for the children. Okay, so this is a 4 node, looks like that. A 3 node looks like this, or this. So notice my red pointer is for the my node partner, and then the black is for the others. Now, on the 5th edition, this is all black and white, which doesn't make any sense. And I always said, why don't they use color for red and black edges? But they did use color. But why didn't they use red? They used blue. Is that like red? Yeah. It's like,
Somebody wants to usually has 9 for production.
I don't know. It's like, okay, you use color. Why didn't you just use red? I
This
don't
red isn't
understand.
throughout the rest of this book either. So
Blue's
maybe they
cheaper.
just-
Blue is cheaper. Okay.
The math book has no problem using math.
Yeah. So, and this isn't even printed, right? What in the book is it printed in color? It's probably not, is it?
It's just blue, black, and
It's still
white.
blue.
Okay.
So that's
All
why
right.
books are so expensive.
So you see how we encode these, right? So this is a BST. This is a binary search tree. We agree, right? All nodes have one value, left and right is honored, and so on. This is a binary search tree encoding of the tree that we had way back here. Oops, here. Figure 920 actually. Where's 920? Oh, there. Of that one, sorry. It's a this is a 2, 3, 4 tree, and this is what that looks like as a red black tree. So it's a BST, but I'm using red and black pointers to show those things. Like this means this would have been a 3 node in the original tree. This is a 4 node in the original tree. Another 3 node, another 3 node. Okay? So, searching and traversing. Searching and traversing are a piece of cake. They're binary search trees. You don't do anything special. You ignore the color of the pointer for searching and traversal. You just have a left pointer and a right pointer, left child, right child, and you just follow those. So you don't care. Now, inserting and removing with your RB tree, red, black, sometimes people call it RB, RB tree, you adjust the insertion algorithms to accommodate the colors. Now, this is what I want to show you. This picture is awful again. If I have green marker, purple markers. All right. All right. This is a 4 node with 4 children, right? 4 children, 3 values. If I was to draw this, I'm going to make this a little smaller. I want a little more. I'm going to draw this same thing using the RB encoding. So I'm going to get medium, small, large, and then I'm going to get A, B, C, D down here. All right, medium, small, and large. Medium and large are connected in the same node, so they use red. And these others are actual real children, so they use black. Okay? So far, so good? All right, now I'm going to split this one. I'm going to split this one to be M, S, L, A, B, C, D. Okay? Let's put that over here. M, S, L, So this is now black. This is black. These are black. All right, what's the difference between this and this?
Can be, well, be
You
treated.
can't tell the difference?
It'd be treated as a 2, 3, 4 and remove.
Yeah,
Treated
but
as an
without
insert.
any of this, what are the differences between these two trees?
A flag.
The edges.
I changed the color. I took this 4 node and I split it by changing the color of those edges. That's all I had to do. So if I had my 2, 3, 4 node tree insertion algorithm, I'm going along and anytime I hit a 4 node, I have to split it. That means I'm going along and my BST, I hit a node and I say, both your children are red. That could sound bad, but both your children are red. We need to make them black. So I want to split that node, so I just change the children from red to black, and then I keep going.
Get out the spray.
That's all I have to do to split those nodes.
You only split 4s, so it's like.
When you're doing that insert, right, you only split the 4s. So it turns out that there are other things like this, other the operations. You know, there was occasionally those merge operations and the distribute operations. They all are almost all of them are accomplished just by changing the colors of the edges. You change the colors of edges in different patterns. So here's an example where you do a color change only. So what I have here is a 4 node. And the 4 node is the child of another parent of a 2 node. And then when I want to split this 4 node and push this up, I just change those to black and I change that to blue, which now means this is a 3 node and these are just 2 nodes. Which is exactly what I wanted to happen. I had a 4 node. Now we need to push a 4 node that was a child of a 2 node, and I needed the 4 node to split and push this up to make this a 3 node. And so just by changing the colors, that's what happened.
You avoid an insert in the process.
Yeah.
This is where you tell us that we're never going to use this.
We're not done yet. Okay, so this is how we can end up splitting a node then just by doing a color change, which is pretty slick, right? That's not hard to do. Now that 2, 3, 4 algorithm wasn't wasted because that 2, 3, 4 algorithm gave us the concept of how we can traverse through our tree and change and split things, which now is just changing colors, but split things so that we maintain balance and we only need to do one pass. Now it does get a little more complicated, but it's the same idea. This is another color change where I'm taking a 3 or a 4 node and splitting it and coming this is just the other side. Sometimes we have to do a little bit of a rotation. In this case, I have a 4 node and a 3 node. And I'm going to split the 4 node, push that up, so now that 3 node now becomes a 4 node. And I can't remember where this comes from. This was a rotation. I don't know why. Honestly, I don't remember. But notice what happened is this Q came down here. And it became, this was a 3 node, now it's a 4 node.
Reverse it.
Yeah, I don't remember why this has to happen. I know it does have to happen on some occasions. So this is another case where we have to go through the different scenarios, but there's a small number of them. And you map out what they need to do, and you look at the different steps. So this is a color change, and occasionally I have to rotate these a little bit. So what happens, I'm not going to go through each of these, but what happens then is using a red-black tree, I can encode a 2, 3, 4 tree. So I gain all the advantages of that 2, 3, 4 tree algorithm, the I mean, what's the primary benefit of a 2, 3, 4 tree?
One
Always
pass.
balanced.
It's always balanced. And then the 2, 3, 4 tree is more efficient, and there's just a 1 pass to insert or delete. There's not a 2 pass to do that. So I have all those advantages. I don't have 4 pointers in every node. I just have 2. I get my standard VST search, and I get my standard traversals. So that is great. I will not tell you that people don't use these, because this is in fact what people use. People